Were you right there? Yeah. You were? Okay. All right, so I asked you to do a quiz. If you have that for me, then I will collect it. So you can either bring it to me or just pass them to the center, and then I'll get them. Thank you. I do not. Just leave it. Leave it. Nope, not that. Don't. Yeah, just make sure your name's on the first one. I should be able to tell. You. Anyone else? Right here. Thank you very much. All right, it's 9 o'clock. Any issues with the quiz? I know at least some of you went to the tutoring lab to get help on it. That's okay. But any major issues? No? Okay, I just posted the video of our class, I think this morning. Sorry it took me so long to do that, but I have no idea how the quality of these videos are coming out, so let me know if they're like completely useless, if they're all blurry, because I just push them out to YouTube. I don't go back and edit them or anything like that, so you let me know, right? I'm only picking up about from here over on the board. So, all right, we ready? We're going to get started. We're going to do 3.6 today. Right now, it's the calm before the storm, okay? We are transitioning ourselves out of Cal 1 into Cal 2. First week or two, it's going to be, stuff that you're like, okay, Cal 2 isn't so bad. And then it's going to just be like, whoa, all right? So I just want you to be prepared. I don't want you to get complacent, all right? If you're feeling good, that's good, but be ready, all right? All right, so last time what we did was we said, okay, we remember in Cal 1 we had the 6 trig functions. I'm sorry that looks so bad over there. Ooh, whoa, okay, try this again. So we have our 6 trig functions from, you have these formula sheets, right? This is what I handed to you. So this is one of your reference pages. We have the 6 trig functions from Cal 1, that's formulas 13 through 18. And those are their derivatives, right? Last class we said, okay, well, we also had inverse trig functions in pre-cal, right? And in Cal 1 we never talked about what the derivatives of those were. So last time we established 6 new derivatives, right? And there they are. Today what we're going to do is I'm going to introduce you to 6 new functions. They're not technically trigonometric functions like the ones from pre-cal. They're called hyperbolic trigonometric functions. I'm going to introduce 6 new ones, 6 new functions to you, all right? Those functions, after I introduce what they are, I'm going to then establish what the derivatives of those are, all right? So what we're going to do by the end of class is we're going to have 6 new functions, right? 6 new derivatives, yes? And then each of those functions, guess what? Has an inverse. So there's going to be 6 new inverses and 6 new derivatives of inverses. So we have, how many derivatives do we have there? 12? Right? We're going to have 12 new ones by the end of today, all right? And then everything we learned in Cal 1, chain rule, product rule, quotient rule, will apply to those new functions. That's the goal. Got it? Okay, I want to motivate the idea first, though, with a little visual aid. I don't do many visuals in this class, but this one is somewhat easy to do. So what I'm going to do is I'm going to hang this string, and I wish I had a colored string. I don't have one, but there's the string. And I'm going to hang it here between 2 points, all right? Like this. Does anyone know what that's called? A hanging string. No. That's a technical name for when you hang something between 2 points or 2 posts, right? Think of like your electrical lines. You know, driving down the road, you see all the lines. Anyone know what that's called? No? It looks like a parabola, doesn't it? Doesn't this look like a parabola? And that's actually the question that we would ask. Well, we as in humans, right? At some point we said, hey, is that a parabola, right? Because we study those in college algebra. Is it a parabola, right? Oops. Hey, come on in. So that's a good question. Is this a parabola? Right? If it is, then there should be some sort of function that would model that, right? And so is there a function f of x equals, what's a generic way I could write a parabola? There's what we call the standard form of a parabola, and there's a vertex form. So I'm going to write it in the vertex form. And if you're sitting there going, what the hell is he talking about? Just let me write it down first. Okay, a times x minus h squared plus k. In college algebra, you should have learned that the equation of a parabola can be written in this vertex form. A represents whether or not the parabola opens up or down, right? If you change A, it kind of widens it, makes it more narrow, right? The H gives you the horizontal shift, and the K gives you the vertical shift, right? So that's like the generic form of a parabola. So the question is, right, is this a parabola? If it is, could we actually find the function that models it, right? Seem like a natural question? All right. Well, I'll spoil it right now. The answer is no. Okay, this is not a parabola, right? It looks like a parabola, but it's not. There is no quadratic function that you could make that would ever draw this exactly. You could get it to like match at a point or maybe a few points, but you couldn't get it to match at every point. So then once we discovered there's no parabola that can do that, we said, all right, well, what does? Like what function does draw this, right? And that is where we come up with these new functions that we're going to talk about today. All right? All right, so that's the motivation. I'm going to put this back up here in a moment because I'm going to turn on the, I don't know if I'll do it there or here, but we're going to try and see if we can get Desmos to draw a parabola over our string. And we're going to see it's going to be impossible for us to do it. And then, y'all know what I mean by Desmos? Desmos is a graphing utility. We're going to use it a lot in here. So we will do that, and we'll see that Desmos is not going to be able to draw us a parabola on top of that. And then we're going to have Desmos draw us one of these new functions from today, and it's going to just lay right on top of it perfectly. Now, I don't know how good it's going to be. I mean, this is a string. It's wavy. It's not perfect, right? So we'll see how it goes. All right? So you ready for the functions? Let's talk about them. 3.6 in the book. Somewhere. There it is. 3.6. So again, as a reminder, in case you weren't here last time or if you were just looking out the window at the birds, the notes I'm going to project over here, but remember these notes are available to you electronically, so you can have your tablet or laptop during class if you want to follow along, if that's hard to see. All right, so we're going to talk about the hyperbolic functions. So we first need to define them. And what you're going to see is, you remember when we were doing the trig functions back in pre-cal, how did we define, like, do you remember, does anyone remember like the first introduction to trig functions, how they were introduced to you, like geometrically? Right triangle, right? The right triangle, and then we start saying like SOHCAHTOA, right? That's how you first start hearing about like sine, cosine, tangent, right? All that stuff. So now I'm going to introduce you to the hyperbolics. And what you're going to see is that they have nothing to do with the right triangle, right? So let's introduce you to them. There are six trig functions which are just a special combinations of exponential functions. So before I scroll down, I just am going to remind you from college algebra, e to the x looks like that, right? It's an exponential function. And then the other one we want to be familiar with is e to the negative x, which is that function reflected over the y-axis. It's just a reflection. It turns out that if we take some combinations of these two functions together, like algebraically putting them together, we get the six hyperbolic trig functions. So it's not related to right triangles, and it's a little weird when you first see them, because we're just going to give you the definition, and that's it. Here's the definition of what they are. So let's do the first one. There it is. I'm going to make that bigger. Okay, there's the first one. And now these are on your formula sheets, okay? They are on your formula sheets. I'm not going to tell you where. You can go find them, all right? But the definitions of these hyperbolic trig functions are there. So what you see there, our very first one, is written sine with an h and then of x. So it's kind of, remember, that x is like the argument of the function. This is called the hyperbolic sine function, or sometimes you can say the sine hyperbolic. It really doesn't matter how you say it, as long as you include the hyperbolic in your wording. So that's called the hyperbolic sine function, and here's the definition of it. What is it? Well, it's the e to the x function. It's that exponential function I just erased, right? It's that one. What? Minus the other one, which is the reflection one. You subtract those two functions, and then you divide by 2. And that is the definition of hyperbolic sine. Now we can rewrite this. We can take the 2 on the bottom, we can write it as a 1/2 out front, and then we get that, which is the second version there, right? So this should be kind of weird, right? It's like, okay, well, where'd this come from, right? Like, it turns out that it was actually backwards. We would see these things appear a lot in different applications in physics. And so what we did is we said, we're seeing this so much, let's define this. Let's actually call this something. And we called it sine hyperbolic. All right? So let's practice with something just to make sure. Like if I asked you right now, what's sine of, put you on the spot here. What's sine of pi over 4? Not hyperbolic. What's sine of pi over 4? Pre-cal. Root 2 over 2. Okay. So we should be able to plug numbers into this, right? So let's try and plug a number into it. And let's start simple. What would sine hyperbolic of 0 be? Well, according to its definition, I'm going to use this one. It would be 1/2 e to the 0 minus e to the negative 0, right? That's what I would do. I just plug in 0 for x. And what's e to the 0? Anything to the 0 is 1. And negative 0 is still 0, so e to the 0 is 1. So this is just 1 minus 1, isn't it? And so this just gives you 0, 1/2 times 0. So you get 0. So sine hyperbolic of 0 is 0. With me? Let's try something a little more complicated. Let's do sine hyperbolic of 2. Plug in 2. You just get 1/2. What? E squared minus e to the negative 2. Just replacing the x's with 2's. And there's nothing you can do to combine these two together now, right? E squared is whatever e squared is, right? You probably have to do that on your calculator. And then what is that? Just so we're clear, this is e squared. You could look at that as 1 over e squared, couldn't you? Like drop that down to the bottom. 1 over e squared is some decimal, right? This is some decimal. You subtract the 2, you get some decimal. You take half of it, you get some decimal. So we would need our calculators to evaluate this, wouldn't we? And we would get some approximate answer. So if we did a decimal on our calculator, we would have to say approximately equal to blah, blah, blah. All right? So I'm not going to carry it out the rest of the way. I trust that you could do this, right? But that's just showing you how to evaluate this function. Good? All right, let's move on. Let's define what cosine hyperbolic is. Well, check out what cosine hyperbolic is. It's almost the same thing, right? There's only one difference. What is it? It's addition right here instead of subtraction. You see that? Everything else is the same. That's the definition of cosine hyperbolic. So the way that I remember it is I kind of memorize the formula, and then I remember that sine hyperbolic s sine is subtract, and then cosine is just not subtract, right? It's add. So, I mean, but you do it however you want, and it's on your formula sheets. So those are the definitions, all right? Now we have, what, 4 more? Tangent hyperbolic. So good news. The remaining 4 are exactly what they were in pre-cal. Remember tangent is just sine over cosine? Well, tangent hyperbolic is just sine hyperbolic over cosine hyperbolic. And secant hyperbolic is just 1 over cosine hyperbolic. So everything else is now just ratios of those two. So let's look at tangent hyperbolic. Tangent hyperbolic is this. So tangent hyperbolic of x is sine hyperbolic x over cosine hyperbolic x, which, if I wanted to write it out, would be 1/2 times e to the x minus, because sine is the subtract one, minus e to the negative x over 1/2 and then e to the x plus e to the negative x, right? I could do that. And cancel the halves or get rid of the halves, right? These are gone. And at this point, you really, I mean, you can't, like I hope, yeah, you wouldn't do that, would you? Right? You're not going to do that, right? You're not, okay, good. We're not going to cancel stuff, right? There's not a whole lot we can do here, all right? There is more, I mean, you can do some algebra, but there's, I mean, I would argue that's pretty clean. I mean, there's nothing else really to do. But let's force something to happen here, just so we can work on some algebra real quick. All right, could I do this? Could I do that if I wanted to? Is that legitimate? Yeah, just dropping these down, looking at these as fractions. Okay. All right, I'm going to write down the next line. Let's see if you can figure out what I did. I multiplied what? I multiplied the numerator and denominator by e to the x. So basically what I was doing was trying to like clear the fractions out. So I multiply the top and the bottom by 1, right? I multiply by 1, that's 1. And then I distributed this through. So what happens when you do e to the x times e to the x? You have to add the exponents, right? X plus x, 2x. This to this, they cancel out, you get your 1. That's this, right? And then same thing on the bottom. Yeah, y'all see that? So this is not a necessary step, but I know a lot of textbooks would go from that to this. So I just want to make sure you see what's happening there. We all right? Okay, I'm not going to go through the others. Cosecant hyperbolic is the reciprocal of sine hyperbolic, and secant hyperbolic is the reciprocal of cosine hyperbolic, and cotangent hyperbolic is the reciprocal of tangent hyperbolic. So everything's just flipped over. All right? Those are your hyperbolic trig functions. There's 6 of them. Let's look at what the graphs of these look like. Do you remember how, do you remember how sine and cosine from pre-cal, those look pretty similar, don't they? Sine and cosine, they're just like phase shifted off by one another. I wonder if these look the same. What do you think? Do you think that sine hyperbolic and cosine hyperbolic look similar? What do y'all think? Probably, right? I mean, what's the difference between them in the definition? Is there a big difference between them in the definition? No, just a sign, right? Just a little simple subtraction sign. I wonder how much that impacts the graph. Well, let's go ask Desmos to graph these for us, all right? So I'm going to go to, if you've never been to Desmos, I'm going to go to Desmos, and I'm just going to type in sine h x like that. That, can you all see that all right? everyone? You see it? That looks nothing like sine, right? That looks nothing like sine. That looks more like a what? What does that look like to y'all? Like a cubic, like x cubed or something? Or it might look even like a tangent, although tangent was periodic. This isn't periodic, but it definitely doesn't look like a sine function, right? That's what hyperbolic sine looks like. Wonder if cosine hyperbolic is going to look similar. Cosine hyperbolic x. What do you think? Same? No? Similar? I don't think those look anything like one another. You could argue there's some similarities, but not like sine and cosine back in pre-calc, right? So very different looking functions. Let's look at tangent hyperbolic. Okay, weird. Okay, back in pre-calc, what was the domain of sine and cosine? All real numbers, right? With sine and cosine, you could plug any numbers you wanted in, right? Tangent, though, had problems. Tangent, remember, was periodic. You had these vertical asymptotes at like the pi multiples of pi over 2, like pi over 2, and then you go back and forward by pi, right? So the tangent in pre-calc had a problem. Does it look like our hyperbolic tangent has any domain issues? No. Okay? So I'm just trying to show you that this is very different than our standard trig functions, right? You can just see it. They're not behaving the way the others did. How about this? Let's do one of these reciprocal. I don't even know if it'll do it. So I'm just going to type it as 1 over sine hyperbolic x. Okay, I'm losing track of where that is. Let me get rid of those. So can y'all see that the one that looks like x cubed, that's sine hyperbolic. And then the blue one is its reciprocal. The blue one is its reciprocal. So the blue one is cosecant hyperbolic. And that cosecant does have a problem, right? You see the domain problem for this one? It happens at 0, right? This is sine hyperbolic. It has an x-intercept right here, which means if you do 1 over sine hyperbolic, you're going to have undefined there, which is why the blue one has an asymptote there. So yeah, you'll see the connection? All right. You do not need to memorize all these graphs, and we're not going to go through an entire study of how to graph these. It's just really to let you see that they are different than the standard trig functions. Do you all want to see the rest or no? Yeah? 1 over cosine hyperbolic. There's that, and I will compare it with cosine. So the black parabola looking one is cosine hyperbolic, and then the greenish one is its reciprocal. And there are no domain issues there. As you can see, the black one the parabola never touches the x-axis, so we never have 0. Zero never comes out. So the reciprocal is never going to have any undefined points. And last one, let's do 1 over tangent hyperbolic. That is the reciprocal of the red one. Hard to see the red one. The red one there, it's kind of getting covered up over here. Its reciprocal is this purplish one. Okay, that's just the pictures. Yes?
I'm sorry, I didn't catch if you addressed it or not. Are there horizontal asymptotes at 1 and -1?
That's a really good question. For this one, for the inverse, or for just the cosine hyperbolic? For tangent hyperbolic. So I don't want to go too far off topic, but do you hear the question? Are there horizontal asymptotes for tangent hyperbolic? What did we say tangent hyperbolic was? Tangent hyperbolic of x was, I wrote it down and then we simplified it, didn't we? Mm-hmm. And when I simplified it, it came out to be e to the 2x minus 1 over e to the 2x plus 1, right? That's what it came out to be. So Chris, I'm going to help you answer your own question here. You're asking if there's horizontal asymptotes, right? Okay. So using Cal 1, we could apply the limit and let x go to infinity on this, and that would tell us what's happening as we go out to infinity, right? Like as we go out, let's just go out to the right side first, all right? So if I take this function, I take the limit, as x goes to infinity of e to the 2x minus 1 over e to the 2x plus 1, then we look at what happens, right? So e raised to the 2 times something becoming infinitely large. This is like e to the infinity. What does that do? Becomes huge, right? Subtract 1, still huge. Same thing on the bottom, infinity plus 1, huge, right? So we have infinity over infinity. What do? L'Hopital, right? L'Hopital. So we would bring in L'Hopital's rule, take the limit as x goes to infinity. How many of you did not see L'Hopital in Cal 1? Did not see it? Did not see L'Hopital? Okay, so get with me because I have a video I can show you. L'Hopital is important, yes? Everyone who's seen it? It's important. Well, it's important. There's a lot of shit with L'Hopital. There's a lot of stuff, but it really helps you. And in this class, I assume you've seen it. And so once you learn it, it's not a big deal. But there's a lot of little nuances, right? If you have like 1 to the infinity, then you have to bring in logs. And there's a lot of little things. What I'm going to show you here is a very basic L'Hopital problem. So what do we do for L'Hopital? Take derivative of the top and bottom separately, right? So what's a derivative of the top? And drum roll. 2e to the 2x. 2e to the 2x, right? Derivative of e to the 2x is itself times derivative of what's up here, which is 2, and then minus derivative of 1 is 0, right? So that's derivative of the top. What's the derivative of the bottom? Same exact thing, right? And now algebraically, that's just 1. So we can just kind of reduce everything out and turn it into 1. So what's our answer? 1. So Chris, does it have a horizontal asymptote? Yes. As you go out to the right, where's it headed? 1. Do you see it in the picture? Yeah. Yes. So that just verifies it. Now, to show the other direction, we would have to go to negative infinity. And that changes things because what happens if you go to negative infinity here? Where does this go? What's e to the negative infinity doing? Getting infinitely small, right? Think about this. E to the negative infinity really means 1 over e to the infinity. 1 divided by a number that gets big gets small, right? So when we change this to negative infinity, this becomes, that goes to 0, right? And that doesn't change. That's negative 1. This goes to 0, and that doesn't change. That goes to plus 1. So we have negative 1 over positive 1, which is negative 1, which is what the picture says, right? Good. That was a nice little review of L'Hopital's rule and limits. Did that make sense to most of y'all? Okay. All right, good question. We are moving on. So I already talked about the hanging wire. I'm going to get back to that. I never gave it a name, okay, but I'll kind of tell you right now that hanging wire I showed you a second ago is called a catenary. Okay, it's called a catenary.
Is that the word you wanted us to guess?
Guess? Well, I said, had anyone ever heard of it, like what it's called? I was just curious, because in physics, you study catenaries and stuff. So I was just wondering if anyone had studied it yet and knew what it was called. So no one said catenary, but that's what it's called. I'll get back to that. I'll get back to catenary. All right, so the hyperbolic trig functions, I already showed you the graphs. We don't need to do that. And I now have an example for you. So before I do this example, I want to remind you of, I know you all know this equation. You've seen it and you know it. What's that equal to? 1, right? That is like a fundamental identity from pre-cal, right? It's called the Pythagorean identity. And there's actually 3 of them, right? There's another one that involves tangent squared, and there's another one that involves secant squared, and we're going to visit those again. But just remember, this is from pre-cal, right? We know this. And this is a similar formula for hyperbolics. How did I do it there? Yes, I put the squared after the h. That's right. Minus So this is true, okay? This is true. That when you take cosine hyperbolic, you square it, you subtract sine hyperbolic squared, you will get 1. We need to show that that's true. So back in pre-cal is probably where you saw this for the first time. When you're trying to show that something is true, what you have to do is start with one side and then turn it into the other side. You're not allowed to work with it like it's true to start. So what I'm going to do is I'm going to start with one of the sides I get to choose, and I'm going to try and manipulate it until it looks like the other side. So normally you start with the more complicated looking side, which would be the left side. So I'm going to start here by writing LHS, left-hand side. I'm about to put the left-hand side of this equation down. And now what I'm going to do is I'm going to see if I can manipulate this algebraically to make it look like the right side, which is, I want to show that that's 1, right? So all I know right now is that I know the definitions of cosine hyperbolic and sine hyperbolic, right? I've been presented with that. So I'm going to rewrite this. Before I do the next line, just again, so we're clear, it's the first week. We're taking baby steps here. We all understand that that notation means that, right? That's what that actually means. And now I replace each of these with what they are. So all I did here is replace cosine hyperbolic of x with what it is by definition, and replace sine hyperbolic x with what it is by definition, right? And now I still have to square those, right? I have to square those. No one has a question? When I square this, right, the parentheses are here, right, and here. When I square this, because there's multiplication here, I square that, right, and then I square that, and I have to multiply the two together. So when I square 1/2, I get 1/4. And then I take my e to the x plus e to the negative x, and I still have to square that, right? I haven't squared that yet. I'm just kind of getting rid of that 1/2 first, taking care of it. And then next to it, I have minus. Again, I'm going to get a 1/4, and then I still have the e to the x minus e to the negative x. I still have to square that. Are we good? Yeah? You ready to square? We have to FOIL, right? We have to take this, multiply it times itself, which means we have to FOIL that out. I'm going to do that over here on the side, just to keep my work nice and clean over there. So this is some scratch work I'm doing. I'm taking e to the x plus e to the negative x, and I'm multiplying it times itself. And now I'm going to FOIL this out. Let's see. Let's start getting some involvement. Y'all look like y'all are tired. So remember, I don't want the same